are moving instead of the workpiece, and it doesn't have to be round, right? You can sort of push any shape you want. And so layer by layer, we're sort of stretching and pinching and pulling whatever shape I want here out of this nut.
So the triangle here is coming out of plane.
That's right.
Which means this one over here, are there any optical lockouts I need to be aware of?
Nope, you can walk right up to it.
Can I walk here?
Yep.
All right, thanks.
Just try not to get between the robot and the sheet. You should be good.
Yes, sir. So this one is pushing.
That's right.
So do you have a force gauge on this end effector?
Yeah, there's load cells on both robots, so you can feel exactly what they're doing. Here, you can see over here what's going on. This is the forces that both robots are feeling right now.
Okay, so can you tell me what colors are what?
Yeah, there's the Z component, the in-plane component, and then green is just the total.
It's pretty easy to understand the forces pushing into the plate, but the in-plane forces are the side-to-side forces as the thing moves around.
So there's robot number 1 here is the one that's pushing, and robot number 2 here is the support that's on the other side. What you could do is you could do this process with just one robot, and you could just sort of pulping metal and basically do a bunch of work by stretching.
But the boundary conditions,
then you load the whole thing up in tension, right? So what we're doing by having a support robot on the other side is you pinch, and so you localize all the force just between the tips. It sort of reduces tension on the sheet and makes it so you can form a lot more accurately.
That's amazing. Okay, what Mark just said was crazy, and I have a little visualization here to try to help me understand it. This is just fabric on a sewing frame. Check this out. If you push against this thing, it's going to tent out, right? Like this is going to deform. Obviously, this doesn't behave like the metal does, but it's going to deform out there. Now, when people work with metal, they use something called braking in order to locally deform the metal past its yield strength, basically. They make a permanent deformation. What they're having to do in this case is, because they're poking on one side, if you were to push so hard that you deform it, it'd tent out. It'd be really weird, right? So they're locally doing it by putting two end effectors right next to each other and just yielding it right there in that little bitty spot. That's really hard to do when you have forces on both sides and everything starts to move. So what they're talking about is wild, because when you break metal, you normally have a rigid datum and you bend over a corner. They don't have a rigid datum. They're moving things around, which makes this complicated. So one is pushing, so I would expect a positive force or a compressive force on that one. And this one, if it was just holding in one position, would you just hold the robot here until it feels force from the other side so that you know that you are actually pinching?
We get pretty fancy about it, where basically, should I talk about all this stuff? Am I allowed to do this?
You said should I let him do it since it's ultimately his authority?
No. I mean, I think Mark knows, yes. Go ahead, continue.
Sure. Yeah, really there's control systems on both of these robots where we can sort of plan their nominal trajectory. That just sort of is the theoretical what they should be doing. They also, they feel the forces, and we use that to update, to make corrections to the trajectory.
Continuous feedback.
Yeah, so one of them is correcting for its own deflection under load, because they're not infinitely stiff. The other one is trying to hit a target pinch force that we set.
In super simple terms, the first robot is supposed to get to a certain point in space, and the second robot is supposed to push at a certain force required to bend the metal. That's interesting, but the problem is once you start pushing at those levels of force, the robot itself starts to bend. So you have to accommodate for that.
You have two robots on a pretty large envelope, right? So the envelope is 12 foot by 5 foot. Getting two industrial robots to be very accurate in this envelope is one task. We have to do through a lot of kind of calibration and proper kinematics. But then the moment they start touching sheet, the sheet will resist it. So, and these robots are pretty new. You can kind of imagine every joint slightly deflects, right? So there are controls and mechanisms that basically compensate for that deflection so the robot stays accurate under dynamic load, right? Sometimes, depending on what sheet you're forming, it can be like 20,000 newtons of force that you're applying. It's like as high as the weight of a truck on a very small end effector on the forming side, right? So being able to, and under those loads, robots sometimes deflect 6-7 millimeters, right? And you want to pinch a sheet that's only 2 millimeters or half a millimeter, so you have to adjust for that. So there's a control loop that uses the force data, some of the other data, constantly figure out how it can stay accurate and pitch the sheet the right way.
You just blew my mind a little bit. There's a lot of math here.
Yeah.
So, is there a robot around this corner?
There's a robot that's not running at the moment, but that's it. Yeah.
Okay, so if I understand what you just said, there's many ways to arrive at this point with this linkage.
Yes.
And if I arrive at this point and apply 5,000 pounds in that direction,
Right.
I'm going to get a certain radial deflection here.
Yes.
I'm going to get a certain radial deflection here. You have to also determine how you get there in order to anticipate the deflection.
Yes.
When you have a robot like this with a lot of different joints, you can be in one location, but you can get there many different ways, right? It's kind of funny, but you see what I'm trying to say. Think about it like this. If you've got 5,000 pounds of force that's in line with this first actuator here, there's not going to be any torque applied to it, right? But if you think about that second actuator, the offset between the force and the actuator will determine the amount of torque that that thing has to resist. And the same thing applies to that third actuator down here, and all of those forces eventually get transmitted down to the base of the robot. If you think about how these actuators work, it's made up of motors and gears, right? If you were to zoom in, you would find that these gear trains are imperfect. If you have a driving gear here, if it were to stop and reverse and go the other direction, you would find that there's play between the gear teeth, and that causes something called backlash. Watch the robot draw this shape. Now think about how the motors change direction at different moments along the polygon. Now think about the loading that's happening in the robot arm as it changes directions. It's a pretty complicated motion control problem, isn't it? Backlash is also something you have to take into account with linear actuators, like this screw system here that's moving this big robot back and forth. When you move one way and then the other, you've got to take into account backlash there as well. Okay, so not only do we have issues with the actuators themselves, we also have issues with the arms themselves. Like think about this. If you've been on a ladder and you've tried to like drill something in really high like this and your arm's all weak because of where you're at, but if you're like up here and you really put your power behind it, you line everything up, but you don't deflect as much and you get more strength out of it. All these things factor in as well. So not only do you have the actuator movements, you have the rigidity of the arm itself.
There's two types of accuracy. Like get the robot to one point, but then also accurately move from one point to another while the forces are changing in the robot. So with the load, now there's an extra, like, okay, the joints A1 not only need to be at 60 degrees, they need to be at 60.1 or 60.2 degrees, depending if at the end effector is facing like a 5,000 pound force, right? And including that into the kinetic calculation.
That's hard.
Yeah, it's fun. It's a fun thing that a robotic team is working. Yeah.
So if this is at 0 degrees and I'm pushing into that, are there many different ways to set up the robot to get there, or is there only one way?
No. So because we have 7 axes, there's unlimited ways to get to that point with different poses, right?
So what do? Do you pick a few things and say this always has to be here, this always has to be here?
No. So there's so many cool things. You can just choose, randomly choose, or you can optimize, for example, for stiffness in certain direction that your force is going to be. So you say, okay, move the robot and the rail so the joints in the most stiffest combination to apply the most amount of force without deflection. So there's like you have a function to optimize at that point, right? And you can kind of part of the kinetics to figure out what exactly you want to do.
You're with the smart dude.
Yeah.
This episode of Smarter Every Day is sponsored by NordVPN, which is a virtual private network that you can use to mask your IP address online. You can get a ridiculous deal right now with Nord if you go to nordvpn.com/smarter. And the reason you don't see it on this piece of aluminum right here is because we're about to manufacture that while I tell you more about NordVPN. While I start by getting this block down to size, I want you to know that the way I use NordVPN is to mask what I'm searching on the internet. I don't particularly want people looking over my shoulder when I'm trying to learn about things I don't know a lot about. Sometimes those are political topics. Maybe they have something to do with health things. I'm wholeheartedly endorsing you using a virtual private network to maintain your privacy online. NordVPN is super easy to use. You can even connect to the internet from different places in the world. There's over 5,400 servers you can choose from in 60 countries. The desktop app has this thing called threat protection. This protects from malicious sites, downloads, trackers, and malicious ads. One account gives you protected access to the internet for 6 different devices, so you can use it on all the things. All right, you can see the URL starting to come to life here, nordvpn.com/smarter. Get a massive discount on the 2-year plan specifically, and you get 4 months free. Go Go check that out. See what you think. It's risk-free because Nord gives you a 30-day money-back guarantee. By the way, NordVPN has a no-logs policy. They don't collect, track, or share your private data. All right, so here it is. If you want to try this and support Smarter Every Day by supporting the sponsor, you can go to nordvpn.com/smarter, like you see on the block of aluminum here. Thanks for sticking around for that build, and thank you for considering supporting the sponsor because you're smart. You know what's going on here, and I'm grateful that you would consider supporting. Okay, that's just all the robot. Now we have to think about the metal itself. If we have a piece of metal and we push on it, it's going to deflect, right? If we hold it at two locations and we push on it, it's going to deflect in the middle, right? What happens if we're holding it here and here and we have to push on it down here? Like you're not in the middle, you're way over here. You're going to get a different deflection curve all along the way. Let's go back to my little funny piece of fabric here, right? Think about that. It's one thing to do it for a beam. That's what's called an indeterminate deflection beam. Civil engineers are really good at that. Think about a plane. It's way different. Like planar deformation is hard. So if I were to push up in the middle of this thing, I were to get a deflection right there in the middle, right? It's going to be different if I'm over here at the edge because you see the angle is different towards the edge than it is towards the middle. It's kind of hard to see this, but this is also something that has to be taken into account when you're doing all these calculations. What do you call it when, if I were to take a sheet and I were to touch in the middle, I would get more deflection than the edge? Is that edge effects? Is that what that's called?
I think we call it like boundary condition effects.
That's what you guys call it?
Yeah, but you're right. Boundary condition affects the accuracy of the parts that you attach. So we have a whole software stack that tries to account for that. So you can imagine, form a part, you can then scan it. Actually, the same robot scans it afterwards.
To do quality?
To figure out, yes, exact quality, or should just figure out what it formed.
To update the model.
And then you were like, okay, I formed this. These are the areas that were off. That means maybe I should have pushed more in some areas and pushed less in some others. You can manually iterate on that, keep generating data, and then later create a model that will tell you, okay, in order to form this geometry in this location in the sheets, you need to actually form a completely different part. And in the end, you can actually get the right part without these things we talked about.
You might overshoot here, undershoot here, just like injection molding or something. All these processes have that. It's actually rolling, isn't it?
Yes. So this is specific one does. There are other ones that we have that roll in different ways.
Like a ballpoint pen?
Yes.
Yeah.
Exactly. There's a spear tip, there's a flat tip. Depending what kind of effect you want to get out of the part, you might want to use different effects.
Different radii as well. If it's a sharp crease, different. Okay.
So that's just the smallest feature that you can do. Like we've done like a quarter an inch diameter or some very fine detail feature. I think these are what, three quarters inch diameter.
Yeah. So this one is just I can't predict where it's going. Mark, you have a complicated program. So yeah, it's rolling along the pointing axis, I'll say.
And you can see at the corners where it sort of changes wall angle, where the tip sort of goes in and out.
At the corners it changes?
Yeah, like right here, it's sort of at the bottom of the part, you'll see it comes out now, and then it'll go back in.
Oh, so I see. So we're moving in the Z.
Yeah, like this wall is steeper than this wall, and now it gets steeper again, so the tip sort of goes in and out there to basically keep the tips perpendicular to the surface that you're forming.
Ah, I see. So even though it looks like it's a 2D operation on any one slice, it's actually a 3D operation the whole way around.
They're planar slices, but the tips sort of move like this, sort of depending on the wall angle that you're forming.
Oh, really?
And we have some fancy non-planar slices too.
Here's show you something actually, a non-planar. So like you're forming on a curved section.
Yeah. So
now you're not starting from a flat sheet, you're forming from a section that's already have forming in it. Now your robot is actually going into a non-planar surface to deform and make another feature out of it.
Oh, that's awesome. So this is what's going to happen?
Yeah, we're doing the face, and then this triangle is the one that's just started over there right now. This whole thing is about 90 minutes. Then it'll do this hexagon part. This one's actually a spiral rather than layers. So there's no...
Oh, I feel the oil.
It's a 1 millimeter pitch, but it's just a spiral the whole way.
Yeah.
And then all of these are actually chained together as a single operation. So the robots will do one, and they'll immediately go over and start the next one without slowing down.
That's interesting, because when I looked at it on the internet, I thought you were going to do one plane and then just move in the Z-axis and do more and more planes, but you don't have to do that.
We can do whatever we can imagine. Like right here, there's a bit of a seam if you look really closely where we transition, but if I do a spiral, then you won't find that on this part.
You transition and you move up.
Like this one is just planar slices, so you sort of do one loop and then you step in and you do the next loop.
Oh, I see.
The other one there is path as a spiral, so it's just a continuous sort of going a little bit deeper.
Is it also faster?
I guess a little bit because you don't have to turn around. So yeah, that one it just kind of goes the whole way.
Can you tell me about the end effector here? This
Yeah,
is
so-
an earlier version, right?
Yeah, so
Did I stand here?
yeah, of course. So the goal is, what we want to do is, even though we are doing sheet forming, really our long-term goal is to build what we call like a robotic craftsman, like a system that works like a craftsman. Like, you can pick up a forming tool, form it, drop the forming tool, pick up a scanner, scan it, drop the scanner, pick up a trimming tool. You can see there's a spindle there.
Is that a ER20?
Yep. Yeah, so the idea is like, you can easily change it. So you can see a tool changer here that can drop a tool, pick up another tool, and just move on to the next operation, right? And that's kind of we're imagining these robots like really working like a craftsman that can pick up tools and do different things.
Okay, so you're not pushing like, oh, you're applying electrical contacts, and then you have the mill here.
So again, once you pick up, it automatically connects through the electrical contacts. And now the robot now has an milling end effector. They can drop this, pick up the forming end effector, and go back to forming.
You have indexing pins to align it, and you also align on the plane. So you have total indexing. And then what's going on here?
So those are actually the bearings that through air pressure they lock into the tool.
Okay.
So once you pick up the slave, these things basically through air pressure come out and then lock into the tool so the tool will not fall.
Oh, that's amazing. And what is this? You told me, but I forgot.
So there are different connections. These are pneumatic connections and these are electrical connections.
Got it.
Right now we do mostly forming and trimming. So we do mechanical trimming. So you can see that tool is in a spindle that allows us to cut the parts after we form them. And then you have different versions of the forming end effector. So that one doesn't have the final end effector that goes into it.
Okay.
It does the forming. The one next to it does. As you can see that the end effector is right in there.
So your tools, are they carbide or is that too brittle?
So we tried bunch of material. Right now, most of our tools the base of it is carbide, but then on top of it we have a coating. That coating is slightly more complicated. We have tried a bunch of different.
That's proprietary?
Yes. So
Okay.
That's a coating that basically allows us to do form many parts without basically destroying the part or destroying the tool.
It's a pretty simple tool, isn't it?
Yes. So the end effector is pretty simple. This is one of our designs. We have multiple designs.
I
This
see.
is one of the designs that we're working on.
Then the coating, getting to that,
That's a secret sauce?
that
It took a while.
it took a while. 7 p.m. running to UPS, get this out,
Even though that's a secret sauce, it really also comes down to the software pieces. Like, for example, if you say get the robots and run them in, just get the geometry, slice it in water lines, and start forming it. The final part is going to be inches off of what you actually make.
Really?
So you have to really account for a lot of different things. We talked a little bit about deflection of the sheet, spring back of the geometry itself, and then the fact that you can also tear. So if you don't put the right amount of compression force between the tips, you might tear the sheet, right? So you get to the fracture limit and you tear the sheet. So combination of all those things are accounted in our software to get you a part that's going to be, very close to your final geometry and not like inches off. So that's, I think, where the real secret sauce is, the software piece.
So when you get done with this thing, you're going to have a fully formed sheet. This is going to be a hood for a truck. It'll be done. How do you get it out of that? Do you like jigsaw it out or?
So the same robot, after it's forming it, scans it, and then maps the scan to the trimming path. So it aligns the trimming path with the scan the best way. Picks up a trimming end effector and trims the part. So you leave a few tabs around the part, and then technicians come in and you cut the few tabs and take it out. But we want to make sure the robot at least does the accurate cutting, so that the part is before you move it. And then you leave a few tabs in, and then you cut those tabs and clean those back out.
So if you had titanium, like back in the day when they were building the SR-71, they didn't know how to work titanium. I saw the glimmer in your eye.
To this day, I don't think they can easily work titanium.
Really?
I think it's just very tough alloy to work. I mean, you figure that out of machine it, but still forming it is very tough. Unless you elevate temperatures, and room temperature is really tough to form titanium.
But in theory, could you use this technology to form it and then go in and cut the rivet holes?
Yes.
And are you very excited about that?
I think those are the areas that we're most excited. Enabling alloys that were just impossible before. I think, for example, for hypersonic, we said SR-71, but all the hypersonic applications that we're, the focus of attention a lot now, and some of our customers, they have a very hard time forming the skin of these aircraft out of, high temperature alloys, titanium, Inconel. We're talking about refractory alloys.
Is this titanium?
This titanium that's already cut out. The part from the customer cut out. But you can see kind of the rest of the sheet. It's actually a pretty thin sheet, super strong.
This is all not part of the part, but this is kind of like the form, I don't know what the word is.
You create enough stiffness around the part that as you're forming it, the part is not buckling.
Got it.
Right?
Okay, so, because I'm pushing here. Okay, wow, that makes sense. Because if I'm pushing right here, so steeper angles give more rigid parts.
Yes. And the deeper it is, it becomes rigid.
You just looked
rigid.
at me.
No, like that.
That's right. And the deeper it gets, also you are more rigid because you have to overcome a little bit of elastic deformation before you get the plastic.
Yeah.
So like if you want to do a very shallow part, it just doesn't work. You're just gonna push the part in and out. Once you go further deep, then you create more rigidity. You can easily overcome the initial elasticity and get the plastic rigidity faster.
My brain's on fire. The rigidity of this support skirt around the part is key, and a keen observer will notice in a lot of these parts laying around the shop, it's not just a flat crease with the back plane, it's actually a wavy gusset because that's a more rigid structure. So if I'm looking at this sheet right here, is the material the thickest it will ever be right here in the plane? And anytime I work, I'm having to move material, so it's going to be thinner.
Yes.
Here, is that true?
Yes. So I think the good law you want to apply is that kind of conservation of volume, right? So as you're going on a higher wall angle, the cosine of your wall angle, or sine of your draft angle, times the original thickness, roughly gives you the thickness you're going to get in the part.
Ed took me to a whiteboard and he explained a complicated concept called restriking. The quickest way to explain restriking is if I want to make a hemisphere in one shot, it'll make the side walls right around the outside diameter too thin. But if you do it in two shots, first you make a cone and you push that cone out, then you'll have more material, so you'll have more thickness on the outside of the hemisphere. If you want to learn more about how this works and a ton of different things that we didn't talk about in this video, I've got a lot of that stuff on the second channel video where we just let the conversation play out and you can get right into the weeds with us and understand all these really cool concepts. It's fascinating. Say that again, that was huge.
You can form parts faster than you can simulate it on a computer. Right?
That is such a big deal.
Yes.
A huge thanks to the folks at Machina Labs for showing us this stuff, incremental sheet forming, or as they call it, roboforming. It's a really cool thing, and I'm grateful that they helped us continue the Smarter Everyday Manufacturing series. Speaking of which, if you're interested in seeing the next videos in the manufacturing series, I have an email list. I'll leave the link in the video description or smartereveryday.com. There's a link to the email list there. It's really simple. I don't spam you, I promise. Finally, I want to say thank you to the patrons of Smarter Everyday. This is such a fun thing I get to do. It's a lot of work, and the patrons make it possible. This community of people is the driving force behind me hitting schedules and like actually having the resources to get it done. I'm so grateful for everybody that contributes to Smarter Everyday on Patreon. If you would like to consider that, I'd be grateful. You can check that out at patreon.com/smartereveryday. Absolutely no pressure here, but it's a really cool thing, and we've got a good vibe going over at patreon.com/smartereveryday. If you'd like to check that out, I'd be excited about that. Anyway, that's it. I hope you enjoyed this, the next video in the manufacturing series, and if you want to learn more, there's more information over on the second channel in the long video. That's it. I'm Destin. You're getting smarter every day. Have a good one. Bye.
רכיבים המזינים הטובים ביותר לחיים הטובים ביותר. הכל בזכות המדע.
At NASA, we choose New Jersey because today's big farm infrastructure is the foundation of tomorrow's life science economy. Having access to the facilities to perform the research and having access to the amenities to not make it necessary the capital needed to invest in building those facilities is of the utmost importance. To be able to step into space that they could almost technically turn the lights on and start doing science, it's extremely valuable. Here you get that big pharma quality space for a fraction of the market rate.
also an elaborate glassmaking technique developed in 15th century Italy, in which pattern-colored glass rods are cut, grouped to form floral shapes, arranged into intricate patterns, then encased in clear crystal. If a picture's worth 1,000 words, these 1,000-flower paperweights speak for themselves. Two Canadian artists craft these Millefiori masterpieces just as the renowned glassmakers of Murano, Italy did centuries ago. A mix containing silica sand, soda ash, and lime is heated to 2,400 degrees Fahrenheit, melting it into lead-free liquid crystal. With a molten crystal post, they pick up a densely colored bar of glass. They roll and shake the white color bar while stabilizing the post with cold water. Then, with a torch, they preheat an aluminum mold of a flower or other motif. Preheating the mold helps the glass flow into it more easily and assume the shape in greater detail. Once they've molded the colored glass, they return to the furnace to encase it in molten crystal. Then they repeatedly heat and shape the crystal with tools and with steam on a wad of wet newspaper until the crystal encases the flower-shaped color evenly. After reheating, they put some molten crystal on the end of another rod and grab the free end of the crystal-encased color. They wait until the glass cools to a specific consistency. Then they begin to pour. They slowly stretch the glass into a thin and even rod, careful not to twist it, as that would distort the flower shape of the colored glass inside. This produces what's called a Murini cane, a clear crystal rod with a colored flower-shaped center. Once the Murini solidifies, they nip it into manageable lengths. Then they take Murini of different colors and designs, cut them into short rods, and bundle them into a pattern called a complex Murini. They preheat the complex Murini in a kiln to prevent shock-induced cracking. They now pick it up with the hot crystal post, and after removing the bundling wires, heat and work the group of glass rods into one. They now stretch this complex Murini into what's known as complex Murini cane. Once the cane stabilizes, they cut it into yard-long lengths, then pull them gradually in a kiln to relieve any stresses in the glass. Then they slice the lengths into pieces 2/10 of an inch, the size required for the Millefiori paperweights. Now, using complex Murini pieces of different colors and patterns, they assemble the paperweight design, placing a unique hand-constructed Murini in the center. This one is a trillium. Next, they encircle the setup with a heat-resistant graphite ring. This holds the pieces in position. After a final adjustment, the artists preheat a white lace-patterned glass base they prepared earlier. This base will serve as a blank canvas for the colorful paperweight pattern. They push the molten crystal onto the base. The ring contains it to the base's diameter. Then they reheat the base, making it smooth and free of air pockets. Preheat the complex Murini setup and stick the base onto it. Like before, the ring contains the spread. Another overall reheating softens the glass and fully fuses all the components. This fills crevices and smooths the surface. Now they return to the furnace to encase this paperweight core in molten crystal. Using standard glassmaking techniques, they work the crystal to a bulbous shape. Then on the bottom, they form a break-off point. A sharp tap on the rod cracks the glass at that point, separating it from the rod. They heat the break-off point and insert a piece of cane bearing the artist's initials. After a 12-hour controlled cooling in the kiln, they grind the base level. Then they polish away the scratches left by the grinding wheel. After a thorough inspection, these magnificent Millefiori paperweights are ready to be shipped to art glass collectors worldwide. Many thrill seekers find zip lines exhilarating. But without the proper braking system, they can quickly become terrifying. Magnetic brakes are hands-free and engage automatically, so there's no need to panic. Just hang on, enjoy the ride, and let the brake take care of the landing.
אחת ההתמודדויות המרכזיות עם המלחמה היא פחדים של ילדים. תפקידו של ההורה התומך הוא לחזק את ההתמודדות העצמאית של הילד